I hope everyone's doing well. I hope to give some insight today into some of our efforts at the University Medical Center Groningen in the Netherlands to computationally model MCADD deficiency in the human liver mitochondrion and to try and get to the bottom of the variable phenotype that it produces. So without further ado, let me get my laser pointer and move to the next slide. So first of all, some brief background on the disease. Most watching would already be familiar with it, but to quickly summarize, what you see on the screen is a scheme of the mitochondrial fatty acid oxidation embedded within the context of the ketogenesis here in purple, the tricarboxylic acid cycle in black, the electron transport chain in black, and the gluconeogenesis in purple in the cytoplasm. Medium chain acyl CoA dehydrogenase deficiency, or MCADD deficiency, is a loss of function of this enzyme responsible for converting primarily medium chain acyl CoAs into medium chain enoyl CoAs in the mitochondrion. It is the most common inborn error of metabolism, as you can see, of the mitochondrial beta oxidation, with the canonical C985A to C mutation, leading to a total loss of MCADD function. And it also has other forms in which it comes, other mutations which preserve various levels of residual activity. But the one we'll be focusing on today is the total loss of function 985A to C mutation. The major clinical challenge for us is the heterogeneity of the phenotypes resulting from this inborn error of metabolism. It has, for instance, been observed that siblings sharing the same homozygous total loss of function mutation can have radically different clinical outcomes. As you see here, this ranges from lifelong total asymptomaticity to sudden, unpredictable, and disastrous onsets of hypoketotic hypoglycemia. One of the likely contributors to the metabolic decompensations that the most severe on this sliding scale of clinical presentation show is the inability, this hypoglycemia. One of the main contributors to this hypoglycemia would be then the inability of the liver to produce sufficient glucose and ketone bodies to keep up with the tissue's energy requirements. The fatty acid oxidation, as most watching would know, connects to the ketogenesis most directly by providing its immediate precursor molecule, acetyl-CoA, as well as the reducing equivalent NADH, which is used for the final reaction in the ketogenic pathway. It connects more indirectly, but still crucially, to the gluconeogenesis by way of the electron transport chain, and this happens via the production of reducing equivalents, again NADH, but also FADH2, or more correctly in the mitochondrion, the electron transferring flavoprotein in its reduced form. They pass via the electron transport chain, where they're used to produce ATP, which can exit the mitochondria and be used in gluconeogenesis. So these are the 2 points of contact between the fatty acid oxidation and the 2 clinical phenotypes in which we are most interested in. And among those 2, we're actually most interested in the gluconeogenesis. So our research question that we are addressing is, what would be the sequence of events that leads to the hypoglycemia in certain patients, but not in others? So the name of the game here really is risk stratification. And we're trying to look at certain feedback loops that might predispose certain individuals with the same mutation towards a more severe clinical phenotype. Currently, parents of MCADD deficient children are advised to avoid fasting for longer than 4 hours for the first 2 months of life, and for longer than 6 hours for babies younger than half a year of age. This, as you might imagine, can cause quite a lot of strain on the children and on the parents, and also on their relationship, since the parents now have to wake the children every 4 hours in order to avoid any potential metabolic decompensations. And this is a particular point which parents of this disease would like researchers to address, because in most of those cases, clinical history has proved that these diseases are not at all dangerous. And it's of interest for us to try and figure out which patients run the biggest risks and need to go through this quite stressful regime of intermittent feeding to avoid prolonged periods of fasting. The care goals, therefore, can be reduced to 4 headlines. First of all, to reduce anxiety by providing better dietary advice, identifying better methods of prognostication, and then also the overarching benefits to the entire field would be for us to further sharpen the tools of deep phenotyping studies for patients with similar diseases. So studies like these can also contribute towards other investigations with similar and with related physiologies, and also that can be addressed with related tools. In order to reach these goals, one must first understand the pathway. One way of compiling the available information on the disease and on the pathway is to build a computational model. The process of building a kinetic model is basically a literature review. Important to underscore here is that modeling is fundamentally a process of reflecting information which is captured in the literature through this prism, which signifies our brains and our best biochemical and physiological reasoning, into a computational model, which serves basically as a quantitative hypothesis, a hypothesis which importantly is also interactive and which is also very good for making predictions that can be tested. So when we speak about a computational model, this is not a fabrication, but really something based on the best that we could extract from the enzymology literature concerning this pathway. The model that we're working with has 3 highlights that I would like to point out. First of all, it's historical, being based on a previously published model by Karen van Ernen, who you see pictured at the bottom there. In 2013, her model was a rat model. And then the work was continued by Anna-Claire Martinez for her PhD thesis in 2019, and this work was passed on to me, and hence there is quite a lot of work historically that has gone into fishing out the best ways of representing this pathway mathematically. It's also extensive, with information from more than 250 articles cited and many, many more that have been discarded. So quite a vast set of literature has been consulted for the building of this model. For each of the enzymes, there is a more or less 20-page appraisal of its function and how its function relates to the other enzymes in order for us to get the best possible kinetic representation. And multiple values were also considered for almost all of the parameters. So we really did go very extensively and deeply through the literature. And then finally, it's also collaborative, with each of the enzymes having been evaluated for the validity of the arguments used by one of my colleagues, all of whom you see pictured at the bottom here. The reactions included in the model are now indicated in this picture. You'll see that the ketogenesis, gluconeogenesis, TCA cycle, and electron transport chain are no longer indicated here. So these are the enzymes that were really modeled in some kinetic detail. And for the sake of time, I'll not go into them into too much detail, except where necessary later on. What is, however, important to note is that our target model readout would be the NADH production flux. So NADH, as you see here and here, is a metabolite or a reducing equivalent which is produced by the pathway in both the long chain and the medium and short chain cycles, and hence is really a readout of different branches of the pathway simultaneously. The combined flux through the mitochondrial trifunctional protein and the medium and short chain hydroxyacyl CoA dehydrogenase is taken as the NADH production flux, and this you'll also see coming back in the figures that follow. The readout can be indirectly measured as oxygen consumption, as the electron transport chain uses these reducing equivalents to produce ATP, and in the process also consumes oxygen. So this is not just a readout which is applicable to both of the cycles in the pathway, but it's also one which opens up some possibilities of direct measurement, as you'll also see coming around later on. A decrease in NADH production flux can therefore suggest both a decreased capacity for gluconeogenesis and for ketogenesis, as explained earlier on, as the reducing equivalents are important for both of those adjacent pathways to be able to produce their final products. So let's have a look at how the model has performed compared to the experimental data. We compare the model to 3 quantitative and 1 qualitative data set. Excuse me, I should still be here. Quantitatively, we looked at the oxygen consumption, the partitioning of acyl CoA dehydrogenase activity between VLCAD and MCADD, and also at the ketogenic flux. You'll see more detail on this coming presently. And qualitatively, we also took a look at the model's performance in predicting the concentration of certain key metabolites. In-house, we have a wild type and an MCADD knockout HepG2 cell line for which oxygen consumption flux was measured in an Ouroboros oxygraph. We predicted the oxygen consumption based on the production of reducing equivalents and compared it to the model predictions as you see in the figure on your right. So the model being built to mimic human hepatocytes, which you see here in yellow, somewhat under-predicted the data that was measured on the HepG2 cells that you see here in blue, but not by much. However, the model can also be adapted to mimic more closely the experimental system at hand. And that is exactly what we did using comparative enzyme expression levels for human hepatocytes versus HepG2 cells. So you can actually insert proteomics data into the model in order to HepG2ify it to bring it closer to the experimental system. We did that, and you'll see in the darker yellow here that the HepG2 model, computational model, actually performs a lot better compared to the experimental data. And crucially, we're confirming 3 things here. First of all, that the model can make valid predictions of what happens in real life. Second of all, that the model predicts at least the differences in pathway flux between the wild type and the knockout accurately. So the difference that you see here is actually quite close to the difference that you saw in the measured data. So that's good, meaning that the knockout of the enzyme, the knock-on effects of that are recapitulated in the model. And third of all, what we also show is that changes in enzyme expression can improve the model's performance, suggesting that individualized modeling of systems and perhaps also of patients, as we shall see later on, can be done with some confidence. More on this point towards the end of the presentation. The second validation comparison was made to an existing data set from Aoyama et al. From 1995. They collected 5 human liver samples, and by using VLCAD and MCADD specific antibodies, they precipitated out the activity of those 2 enzymes in separate assays, and then they looked at the remaining dehydrogenation activity that was left for either palmitoyl CoA or octanoyl CoA substrates. So what you see here again in yellow is the simulation data from the computational model, and in blue, the measured data from the paper by Aoyama et al. So they measured the remaining palmitoyl CoA dehydrogenase activity and octanoyl CoA dehydrogenase activity, as you see here, in 2 different conditions, with only VLCAD active or with only MCADD active. And you'll see that the model, the computational model, quite accurately mimics the behavior that they also saw in their system. And this is also good validation that we got some of the kinetics correctly. Then we evaluated the model's ability to simulate ketogenic flux. Fletcher and colleagues used a stably labeled isotope to track flux through the ketogenesis in adult humans after a day of fasting. And the results are pictured on your right. You can see that the model being stoichiometrically adjusted to predict ketogenic flux. So you see that here in the yellow, the readout is still NADH, but this is converted to ketogenic flux using elementary pathway stoichiometry. And it actually rather accurately recapitulated the data in blue, which was measured by Fletcher et al. You can see that it is of the 3 comparisons that we've made, the worst comparison, but still astounding that it can get so close given the amount of steps of recalculation that was done. So we consider this actually quite a striking validation of the models, of the order of magnitude of the model's readouts. So we think we're at least in the right ballpark with what we're predicting. Next of all, we move on to what the model can say about MCADD deficiency specifically. First of all, a note on how an MCADD deficient model is made. All enzymatic reactions in this model, pictured here, are expressed with Michaelis-Menten rate equations, all of them containing a Vmax, which I assume everybody watching would know. An MCADD deficient model, for the purposes of this presentation, is a computational model for which the Vmax of MCADD is set to 0, which will make the effective rate through this enzyme also 0. And that's how we make the knockout or the deficient version of the model. The starting metabolite of the pathway, cytosolic palmitoyl-CoA, selected to represent the availability of saturated fatty acids in the cell, was systematically varied, as you can see on this x-axis, systematically increased through both the control and the MCADD deficient models. You can see that the MCADD deficient model predicts a significantly lower flux at higher palmitoyl-CoA concentrations, and it even has a slight downward slope. So it starts diverging from the control model only at a, let's say, once the substrate concentration starts increasing, then the two diverge. And you can see that as a reaction or a differential reaction to metabolic stress. This is reminiscent of a similar simulation done in a previous version of the model published by one of my predecessors. The main difference here being that the current model is based on data from humans and the previous one is based on data from rat, which was then computationally adjusted to a mouse model. And I think I would also be remiss not in mentioning that this predecessor was Karen van Eunen, who also made the first fatty acid oxidation model, as I explained earlier on. The similarity of the two curves up until this point, after which there is this divergence, with the failure of the MCADD deficient model to maintain a high flux at high substrate concentrations, can be regarded as a threshold phenomenon. In MCADD deficiency, the metabolic decompensations are usually sudden, and we propose that the origin of these episodes might follow also a threshold pattern, whereby sick and healthy individuals cannot be distinguished from one another until a certain threshold is crossed. We can actually compare simulations to the available data from MCADD crises to see if we recapitulate anything observable in the patients in our computer model. What you see to your left is a bar graph of acyl-CoA concentrations in the mitochondrial compartment of the model, simulated under crisis conditions as best we could estimate it. And in this case, we chose a high palmitoyl-CoA concentration, as I explained in the previous slide. Inserting patient urine acylcarnitine concentrations, for which the axis is shown to the right of the figure, although admittedly acylcarnitines in the urine are physiologically quite far removed from acyl-CoAs in the mitochondrion, we do clearly see that there is no accumulation in the patients at the points where you do see the accumulation in the model. Now, to prove to you that my choice of axis size was not arbitrary, if you include crisis samples, you'll see that you find the accumulation of C6 and C8 esters at exactly the same spots as you see them in the computational model. So even though these two readouts are physiologically quite distant from one another, it is quite striking that you see this agreement in the crisis scenario, confirming that we are at least moving towards something crisis-like in the inputs that we give the computational model. You suddenly see this accumulation of C6 and C8 acylcarnitines, as I mentioned, but a slight bump, for instance, in C4 acylcarnitines is not recapitulated by the computational model. That's not a crisis for us as the modelers, because the model is not perfect and need not be perfect to show some important hallmarks of crisis. So we consider this a victory in modeling the disease. Finally, we take a look at the key prognostic marker, used in the clinic, the ratio of C8 to C10 esters. In the model, we again use mitochondrial acyl-CoAs, where blood acylcarnitines are used in the clinic. Again, physiologically distant from each other. But again, you see that the control simulation that we have here lies well under the ratio of 5, which is used clinically to distinguish true from false positive cases, whereas the patient lies well above this threshold. And this again contributes to our confidence that we are somewhere close to a crisis in what we're simulating. But where do the properties of the MCADD deficient model come from? Our suggestion is that MCADD deficiency is an acute castor disease. What is a castor disease? Grant Mitchell published a lovely paper in 2008, before I had entered the sciences or university, in which he suggests that this grouping of diseases, based on shared characteristics. Coenzyme A sequestration, toxicity, or redistribution entails a class of diseases that show an accumulation of CoA esters, which can be potentially toxic, as well as a reduction in free coenzyme A or acetyl-CoA, which can have the effect of disastrously depleting the free CoA pool, or of disturbing the vital regulatory acetyl-CoA to free CoA ratio. This classification can group together diseases that have similar manifestations despite being located in different pathways, and, as I will argue, seemingly related diseases can also be distinguished based on differences in their manifestation. Mitchell and colleagues made the distinction between chronic and acute castor diseases. Let's briefly review some properties of each. Chronic castor diseases lead to a failure to thrive, to chronic symptoms, and to continuous elevations of metabolites in the blood and in the urine, whereas acute castor diseases are typified by extreme illness, often comas, acidosis, hypoglycemias, and hyperammonemias, possibly also with multiple organ failure. Based on these properties, I argue that VLCAD deficiency is more typical of a chronic castor disease, whereas MCADD and SCAD deficiency are more typical of acute castor diseases, whereas these categories are not mutually exclusive, but should be seen as different points on a spectrum of castor acuteness. But we think that this is an important and a relevant distinction to make. For the following couple of figures, the following dimensions of variation were simulated. Increasing palmitoyl-CoA concentrations, which would be then a proxy for increased mobilization of fatty acids during metabolic stress, like cold exposure or intense exercise or prolonged fasting. Increased non-mitochondrial fatty acid oxidation CoA sequestration. So this would then be a shorthand for the increased sequestration of CoA in pathways that are not modeled in our fatty acid oxidation model. So you would also see some of the CoA in the mitochondria going to the TCA cycle, the branched chain amino acid oxidation, ketogenesis, and others. And then thirdly, we'll also vary the activity of the acyl-CoA thioesterase, which I will be calling ACOT for the purposes of this presentation. So ACOT expression then is commensurate to something like CoA liberation. So as you have pathways that consume CoA, you also have pathways that liberate them from their bonds. And this is what we try to capture in our variation of ACOT expression in the pathway. So first of all, palmitoyl-CoA. The black line that you see here is the response of the control model to the simulated increase in palmitoyl-CoA concentration in our computational model. If you lower the Vmax of VLCAD to 10%, we did not use 0% as it leads to virtually no flux through the pathway, and it's also clinically rare, so we chose for 10% in this case. You see a loss of almost 75% of the NADH production flux. If you completely abrogate MCADD activity, you see a different pattern. At about 50 micromolar of palmitoyl-CoA, the MCADD model and the control model are virtually indistinguishable, after which the MCADD model slowly starts moving closer and closer to the phenotype that you see in the VLCAD model. SCAD mimics the control model for even longer and never decreases quite to the level of the MCADD deficient model, in keeping with the relatively milder phenotype of SCAD deficient patients. Taken together, these data suggest that MCADD and SCAD have a threshold behavior of a sort that VLCAD does not, perhaps relating to the onset of metabolic crises also in these patients, whereas these patients are just chronically ill. Next, we look at reducing free coenzyme A by increasing its sequestration outside of the pathway that we have modeled. So the idea here is simply to reduce the amount of CoA available to the fatty acid oxidation and in order to localize the trigger of the threshold behavior to CoA depletion and flux decline. We made a rough calculation of some realistic amounts of CoA esters that would be sequestered elsewhere, and you'll see that we find a value of about 1.8. So we took as an intermediate value of CoA sequestration outside the fatty acid oxidation 1.8 millimolar, as a mild amount 0, and as an extreme amount 2.5. And if we show this on a bar graph, we see that the VLCAD model has a consistently low flux and that the others have high flux at the mild and intermediate sequestration levels, whereas MCADD shows this behavior of a sudden drop in flux when you increase it from an intermediate to an extreme amount of CoA sequestration. So by increasing the burden of CoA sequestration, you push the MCADD model kind of over the edge, and you'll see that this also correlates with the MCADD model having the lowest free CoA concentration of any of the models. So the decline in flux correlates then also with CoA depletion. Finally, let's look at the effect of increasing or decreasing ACOT activity. ACOT, or the acyl-CoA thioesterase, as I mentioned, cleaves an acyl-CoA ester into a free fatty acid and a free CoA. This reaction is irreversible in this model. And if you increase its activity in steps, you'll see that the MCADD model has more and more flux capacity as you increase the activity of ACOT. So looking at the data, you'll actually see that the VLCAD and SCAD models are not affected by this increase. This suggests that in vivo, there might be a potential rescue for NADH production flux by poaching fatty acid oxidation intermediates from the fatty acid oxidation by, for instance, ACOT. You can also clearly see that this correlates with the concentration of free CoA in the computer model. So it seems that the range of free CoA in which MCADD finds itself is also the range in which freeing up free CoA has a greater effect than the cost of having some of the pathway intermediates simply being cleaved off their CoAs and not being oxidized. Finally, we'll have a look at the insertion of some patient-specific proteomics into the computational models in order to individualize them to specific conditions to see if we can find some of these differences that we saw in the theoretical model, also when we insert real patient data. So to try and localize some rescues when comparing asymptomatic to symptomatic patients. The patient data come from two of my colleagues, Anna-Claire Martinez and Emily Jager. They retrieved fibroblasts from 6 control, 1 asymptomatic, and 4 symptomatic MCADD patients. The MCADD fibroblasts all had the same mutations, which leads to a total loss of function. These fibroblasts were cultured and subjected to targeted proteomics. And this provides us with a lovely data set that can be used to adjust the Vmaxes of the model to individual people in order to make person-specific models. The figure you see is the predicted NADH production flux of the computer models adjusted to one person's fibroblast proteomics. Interesting to note here is that these simulations were done with ACOT activity reduced to 10% of its wild-type value, with ACOT not included in the proteomics data, so not affected by the individualization, and at 1 millimolar of non-mitochondrial fatty acid oxidation CoA sequestration. So this is a combination of a very severe ACOT deficiency and a mild CoA burden. And it can be seen that the symptomatic patients have significantly lower NADH fluxes than the control group, whereas the asymptomatic patient does not. Interesting to note here, or important I think to note here, is that although this asymptomatic patient is a single patient, the reason why you see error bars is because 3 fibroblast cultures were made and the proteomics data of a single culture were considered as a single biological replicate. So from there, that you have also error bars in that case. Comparing the free CoA concentrations between these models, the symptomatic and asymptomatic groups statistically significantly differ from one another at high Palmator CoA concentrations, tying the observed effect of NADH production flux decline also to a decreased availability of CoA in the case of the symptomatic patients. Interesting to note is that none of the proteins adjusted in this model, except for MCADD, differed significantly in the primary data set, but including all of the data together in the final simulation does produce a significantly different outcome, perhaps hinting at global adaptations rather than single smoking guns that might account for why one patient might be at greater risk than another. So in summary, we've made a computer model of human liver mitochondrial fatty acid oxidation, and we can predict some key outcomes using it. Using MCADD induces the model to exhibit key disease characteristics. MCADD also shows properties of an acute castor disorder in a way that VLCAD does not. So increased metabolic stresses really push the MCADD deficient model towards CoA depletion and disastrous flux decline. And finally, you find also some of this threshold behavior, so this being pushed across the threshold behavior when you insert patient proteomics of symptomatic patients. And you don't see that same behavior when you insert the data of asymptomatic patients. So we do see a comparatively milder phenotype when we individualize the models to asymptomatic patients, which we find very interesting and hope to expand more on in our work later on. So I'd like to thank everyone that contributed to it, especially to Barbara Bakker, my supervisor.
Great. Yeah, Christoph, thank you very much for that presentation today. I think it was wonderful. And I wanted to say, if there were any questions or comments, how could people reach you?
They could reach me via email. That would probably be the best to me, or perhaps my supervisor, Barbara Bakker. She would probably like to be the first point of contact.
Okay.